Okay, in today's presentation, we're going to discuss the feature pyramid networks for object detection. So here is the table of contents. In most previous object detection algorithms, only the top feature map in the convolutional neural network is used for prediction. In convolutional neural networks, the feature maps of the shallower layers have higher resolution and more accurate object positions, but contains less semantic information. On the other hand, the feature maps of the deeper layers are semantically stronger, but the resolution is low and the object positions are relatively rough. However, for most of the object detection tasks, both rich semantic information and accurate pixel position information are needed. Besides, the feature map in deeper layers are usually compressed to a very small size that may be even smaller than that of some small objects, which makes detecting small objects very hard. Therefore, merging the feature maps of both shallower and deeper layers and recognizing objects in different scales is necessary. Actually, identifying objects in greatly different resolutions is a fundamental challenge in computer vision. There are several ways for object recognition tasks in vastly different scales. The first one is featurized image pyramid. As shown in Figure A, by compression and enlargement in image scale, one input image is transformed into multiple images with different scales. These images are separately input to the model, and the model gives out a set of feature maps. That set of feature maps is a feature set that can represent information in different scales. These pyramids are scale invariant in the sense that an object scale change is offset by shifting its level in the pyramid. Intuitively, this property enables a model to detect objects across a large range of scales by scanning the model over both positions and pyramid levels. However, featurizing each level of an image pyramid makes the inference time increases considerably, and training deep networks end-to-end on an image pyramid is infeasible due to the memory limitation. Therefore, it is very difficult to apply this approach in practice. As shown in Figure B, some approaches use only the single top feature map for faster object detection. Though this approach detects the object faster, it obviously makes detecting small objects very difficult. On the basis of single feature map, the pyramidal feature hierarchy uses multiple features maps that are close to the top layer separately for object detection, which means that the feature map at each layer predicts the detection in the corresponding scale separately. However, the problem of this method is that it forces the different layers to learn the same semantic information. But actually, the semantic features at different layers correspond to different levels of semantic information. The shallower layers have high resolution and learn details, while the deeper layers learn semantic features more. Therefore, the main motivation is to solve the following research questions. How to learn multi-scale feature representation with strong semantic information. The second question is how to use common features for subproblems in object detection, such as object proposal, instance segmentation, and more, that requires features in different scales. And the third question is how to make object detection in different scales efficient in both computational time and memory. The first related work is hand-engineered features and early networks. Before, convolutional neural networks are used for computing shallow networks or image pyramids for face detection across scales. Then, SIFT features were extracted by scale space extrema and used for feature point matching. HUG features and later SIFT features were intensively computed over entire image pyramids. The SIFT and HUG pyramids have been used in a majority of tests of image classification, object detection, and more. The interest of featureless image pyramids rises fast. The second trend is deep convolutional neural network object detectors. With the development of modern deep convolutional neural networks, advanced object detectors using deep convolutional neural networks such as OverFit and RCNN achieve significant improvements in accuracy. In OverFit, The convolutional neural network is applied as sliding window detector on the image pyramid. The RCNN adopts a region proposal-based strategy where each proposal was skew normalized before classifying a convolutional neural network. The SPPNet shows the more efficiency on feature maps extracted on a single image skew in such region-based detectors. Recent, more accurate methods such as fast RCNN and faster RCNN promote to use single skew features since it provides a good trade-off between accuracy and efficiency. However, multi-skew detection still performs better, especially for small objects. And the method using multiple skews. The FCN sums partial scores for each class over multiple skews for computing semantic segmentation. The hypercolumns apply similar ways for instance segmentation. Differently, some approaches concatenate features of multiple layers before prediction. The SSD and MSCNN predict objects at multiple scales of the feature hierarchy without combining the features. Recent methods exploits lateral and skip connections associating low-level feature maps across resolution and semantic levels. There are two main parts of FPN. The bottom-up pathway as shown in the left part of the picture and top-down pathway as well as the lateral connections as shown in the right part of the picture. The bottom-up pathway is a straightforward computation of the backbone convolutional neural network, which computes a feature hierarchy consisting of feature maps at multiple scales with a scaling step of 2. The scales that produce output feature maps of the same size are caught in the same network stage. One feature pyramid is defined for each stage, and the output of the last layer of each stage is the reference set of feature maps. The feature pyramid is constructed using such reference sets of feature maps. The reason for choosing the output of the last layer of each stage is that the deepest layer at each stage should have the strongest features. Specifically, the feature activations output by each stage's last residue block is used for the network structure. The outputs of the last residue blocks are denoted as C2, C3, C4, and C5 with stride 4, 8, 16, and 32 with respect to the input image. The first convolutional layer is not included because it is large memory footprint. Then, the top-down pathway hallucinates higher resolution features by upsampling the semantically stronger feature maps from higher pyramid levels. For upsampling, the nearest neighbor interpolation method is used. These features are then boosted with features from the bottom-up pathway through the lateral connections. Note that each lateral connection merges feature maps with the same size from the top-down pathway and the bottom-up pathway respectively. The merge operation is achieved by element-wisely summing the feature map from the bottom-up pathway after a one-by-one convolutional layer for reducing channel dimensions, and the upsampled feature map from the top-down pathway. This process is iterated until the finest map is generated, and a 3x3 convolution is applied on each merged feature map to generate the final feature map at each stage, which can reduce the aliasing effect of upsampling. The final set of feature maps is denoted as P2, P3, P4, and P5, corresponding to C2, C3, C4, and C5 at each stage. There are two main applications of FPN. The first is using FPN for RPN. The RPN generates 4 entries on the feature map for object detection. Each feature map generated by FPN is followed by one 3x3 convolutional layer and two 1x1 convolutional layers, which is defined as a network head. Since pyramids have the skew information, it is not necessary to have multi-skew entries on the particular level. Therefore, entries of the single skew are assigned to each level. During training, the setting of positive and negative is the same as that of RPN. Any ground truth with IOU greater than 0.7 is regarded as positive, and that with IOU less than 0.3 are regarded as negative. The second application is using feature pyramid networks for fast RCNN. There is a process of mapping a region of interest onto feature maps in fast RCNN. In FPN, this process involves into the need to determine the merged feature maps that map ROIs to different layers of the pyramid. If the size of ROI is relatively small, it is mapped to the final resolution level. And if the size of ROI is relatively large, it is mapped to the coarser resolution level. The feature map of FPN is first considered to be generated by the MH pyramid, then use the MH pyramid method. Assuming that the weights and height of ROI on the input MH are W and H respectively. The parameter K mapped to the PK layer is determined by the following formula, where the number 224 is the standard input MH size for MHNet pre-training. The faster RCNN extracts the feature map of C4, so we set K0 to be 4 to prevent the generation of decimals for rounding operations. The classifier and regressor in fast RCNN are simply referred to as a head, and all head parameters are shared. For the results, Table 1 shows the performance of RPN with FPN. By comparing A, B, and C, we can see that FPN is indeed effective. By comparing A and B, it shows that the detection performance of small objects becomes worse in deeper layers, and the detection performance of larger objects becomes better. By comparing D and E, it shows that lateral connections are very necessary. By comparing F with C, the performance of using only the last layer of P2 is not good as using P2, P3, and P4. By comparing F and C, it can also be found that due to the relatively high spatial resolution of P2, there are many entries. It can be concluded that just using a lot of entries is not enough to improve the accuracy. Table 2 shows the performance of fast RCNN with FPN. Similar to RPN, the results from A, B, and C show the effectiveness of FPN in region-based object detection tasks. The difference between C and F is small because the ROI pooling is not sensitive to the scale of the region. Therefore, we cannot simply conclude that the method of F is not good. The result of faster RCNN is similar, which is shown in Table 3. Table 4 shows a comparison between FPN and other top algorithms. We can notice a significant improvement on the performance of detecting small objects using FPN. So in conclusion, the FPN algorithm uses both high-resolution features with less semantic information and semantically strong low-resolution features to achieve effective prediction by merging the features of these different layers. And the prediction is performed separately on each merged features layer, which is different from the conventional feature fusion method. There are several questions and answers regarding FPN. Question 1. Why can feature maps of different depths be added directly after upsampling? This is due to the end-to-end training. The parameters of different layers are not fixed, and different layers process end-to-end training to the supervisor at the same time. So the added training can be more effective for integrating the information in shallower and deeper layers. The second question is, why does FPN improve the detection performance of small objects? The deep level feature map provides more semantic information, and the shallow level feature maps provide high resolution small objects. Merging the deep level feature maps with shallow level feature maps can make the performance of detecting small objects better. The third question is it possible that MH pyramid will perform better than feature pyramid if time is not considered? Well, the answer is yes, but we do not suggest. It is possible if the training is fine-tuned, but the main problem of MH pyramid is that it takes too much time and memory. and feature pyramids can solve the problem of multi-skill detection with almost no extra calculation. Then, there are further open questions and ideas. First, simple addition or concatenation is used for merging the feature maps in shallower and deeper layers. Are there any other advanced ways for feature map merging that can further improve the performance? The second question is it possible to intelligently add weights on the feature maps in shallower and deeper layers to determine which part has the larger proportion? Following this question, how to determine the weights of the feature maps? Can we use fixed weights or using learning from adaptive networks? Well, that's all for the presentation. Thank you for listening.